The standard error of the regression. The standard error of the regression, capitals SER, or all bigs, big S, big E, big R. The standard error of the regression is an estimator of the standard deviation of the regression error U sub I. The units of U sub I and big Y sub I are the same. So the standard error of the regression is a measure of the spread of the observations around the regression line, measured in the units of the dependent variable. For example, if the units of the dependent variable are dollars, then the standard error of the regression measures the magnitude of a typical deviation from the regression line. That is, the magnitude of a typical regression error in dollars. Because the regression errors U sub I through U sub n are unobserved, the standard error of the regression is computed using their sample counterparts. The ordinary least squares residuals U sub I hat through U sub n hat, that is, the ordinary least squares residuals U sub 1 hat through U sub n hat. The formula for the standard error of the regression is the standard error of the regression equals S sub U hat equals the square root of S sub U hat squared, where S sub U hat squared equals 1 over n minus 2 multiplied by the sum from I equals 1 to n of U sub I hat squared equals the SSR, which is the sum of squared residuals over n minus 2, equation 4.17. And recall that the sum of the squared residuals, this is a reader's note, recall the sum of the squared residuals is equation 4.15 and is the sum of I equals 1 to n of U sub I hat squared. Where, continuing the text, where the formula for S sub U hat squared uses the fact proven in Appendix 4.3 that the sample average of the ordinary least squares residuals is 0. The formula for the standard error of the regression in equation 4.17 is similar to the formula for the sample standard deviation of y of big Y given in equation 3.7 in section 3.2, except that big Y sub I minus big Y bar in equation 3.7 is replaced by U sub I hat, and the divisor in equation 3.7 is n minus 1, whereas here it is n minus 2. The reason for using the divisor n minus 2 here instead of n is the same as the reason for using the divisor n minus 1 in equation 3.7. It corrects for a slightly downward bias introduced because 2 regression coefficients were estimated. This is called a degrees of freedom correction because when 2 coefficients were estimated, beta sub naught and beta sub 1, 2 degrees of freedom of the data were lost, so the divisor in this factor is n minus 2. The mathematics behind this is discussed in section 5.6. When n is large, the difference among dividing by n and by n minus 1 or by n minus 2 is negligible.